Welcome to this new part of the course on statistical mechanics. We will be talking about quantum statistics or quantum statistical mechanics. And so far we have seen the classical statistical mechanics, the formalism of it, which mainly included calculation of the partition function, and from there on one can get the free energy, entropy, specific heat, magnetization, susceptibility, pretty much everything that an experiment or a physical system can give about itself. So, we have seen a number of such systems, and we have calculated various sort of properties, physical properties of these systems. We haven't made any mistake, and those classical statistical mechanics seem perfectly fine. It's only that at large temperature. Okay. So, the temperature has to be large, and in addition to that will also pose another constraint on the density of particles in some time. But before that we wanted to study now quantum stat mech, which should include the indistinguishability of particle. So far in classical statistical mechanics, the particles were distinguishable. Each particle of the gas, ideal gas, as if they were distinguishable, and we could identify them either by their name or by their color or by texture or something. Now, that is not possible here. Now, we of course did not make a mention of this particle in a gas or that particle in a gas. What we mean by identification or by the distinguishability is that if you actually interchange two particles, this is taken as a new state. Okay? And in quantum mechanics, it is not a new state, it only differs by a phase factor, and the phase factor could either be 1 or -1 and things like that, which means that this exchange of two particles in a quantum mechanical system has to be dealt with care, and it does not give you a new state of the system or new microstate of the system, and it is related to the original state by just a phase factor. Okay. So, this is the crux of indistinguishability that we have to talk about, or we have to incorporate in our system and develop the quantum statistical mechanics. This is the main idea of quantum statistical mechanics, that the indistinguishability was not taken into account in classical mechanics, and which was fine, as we have said earlier, that at large temperature or at very low densities of the particles. We will show how the density come into the picture. Those things that we have learnt earlier, they all seem fine. Now, we have to modify each one of them and incorporate this indistinguishability. Okay. And a step towards that had already been taken by this Sackur-Tetrode equation. So, we will just briefly introduce the Sackur-Tetrode equation, or which is a formula for the entropy of an ideal gas, monatomic ideal gas. But before that, let us try to go a little history of how quantum mechanics was developed and what necessitated the introduction of quantum ideas, which were preliminarily done by a large number of people. Let us say only we are going to talk about Planck of these very large number of people who have contributed significantly to the development of the subject. So, the way quantum mechanics developed is that there was this black body radiation, which was seen that you have the intensity versus the wavelength, that for these black bodies they seem like this, which means that the intensity of the emitted radiation versus the wavelength of the radiation is it looks like this non-monotonic curve that I show here. And this was a bit of a surprise, because why it shows a non-monotonic behavior, because this part was nicely explained earlier and this part is nicely explained earlier as well. So, there are two monotonic functions, one we call as a Wien's law, the other is called as a Rayleigh-Jeans law. And these two actually nicely explain the either the lower lambda region or the higher lambda region, but none of them actually have a upturn and going down. And so, what we are talking about is that you take a metal and you heat it up, and initially when you start heating it up, it starts getting hot. First is it becomes red hot, and then it becomes white hot, and so on, which means that the intensity of the emitted radiation actually changes its wavelength from some red to blue and so on, or to white and so on and so forth. So, that means that this intensity of the emitted radiation versus wavelength, when you try to plot it, it shows this formula. And so, the Wiens and the Rayleigh-Jeans law, they were unsuccessful in showing the upturn and actually reproducing the experimental observations, and Planck came and fixed it a bit out of desperation, and also by his intuition that what should it be. And he said that look, I mean, all these the emission or absorption of electromagnetic radiation happens in terms of packets which are called as photons, or these packets, or this quantum of this radiation is they are called as photons. And so, all these exchanges, either emission or absorption by any body in presence of an electromagnetic radiation, it happens in the unit of h nu or h cross omega. And then he wrote down a distribution function which correctly reproduces the intensity of the radiation. So, you calculate the average energy with that distribution. We have seen how average energy is calculated with the aid of a distribution. So, Planck gave you a distribution formula, and then you plug in this h cross omega, multiply it by that distribution, and integrate over all frequencies or all wavelengths. I mean, frequency and wavelength are related, and then you can get this, you multiply it by the speed of light, which is c, or the speed of the electromagnetic radiation, and you get the intensity. So, the intensity correctly gets reproduced by this, and this was a birth of quantum theory. But now, we are not here to discuss really the development of quantum theory, but the Sackur-Tetrode equation, which was the first step towards understanding of these indistinguishability of particle, and working out the entropy of a monatomic ideal gas correctly by taking into account this indistinguishability. So, that was like the first step, which was independent, completely independent of this Planck's radiation formula or Planck's ideas, and it is also independent of this the Einstein's concept of quantization for the photoelectric effect and so on. So, it is really an independent effort from the thermodynamic point of view or from the statistical mechanical point of view, that such a development had taken place, and we will actually talk about this this equation or the formula for the entropy of the monatomic gas. Okay. So, this is not relevant. So, let me just rub it out and let us write down Sackur-Tetrode equation. As the name suggests, there are two people, Sackur and Tetrode. They have independently actually came up with this equation in about 1912. So, it is more than 113 years or 112 years from now. And so, what they did was that they wrote down the entropy of a gas or monatomic gas, and the way they did it is that they have taken this z, which is a function of t, let us write it as beta, and this is like sum over k exponential minus beta E k. I am writing it as E k, where E k is equal to h cross square k square over 2 m, where it is p is equal to h cross k. So, which means that all these things were already in place, and these the fact that we are using h cross, there was a hint. In fact, it was initially developed from the microcanonical perspective, however, we are doing it from the canonical point of view. So, once you write this down and have to evaluate it, what you do is that you convert it into an integral, and you write this down as e to the power minus beta e k, and then you have a dk, and this is nothing but equal to v over 2 pi whole cube and whole cube and 4 pi square, and then you have a 0 to infinity, and you have a k square e to the power minus beta h cross square k square over 2 m and a dk. Okay. And really there is nothing new that we have done. We have simply trying to calculate the canonical partition function, and once we do that, I will not show you this derivation, but you can do it yourself. This is very simple. This is a double derivative of the Gaussian formula that we have already given. So, what we can say is that if you have a quantity like this, x square e to the power minus x square or alpha x square, say alpha x square dx from say 0 to infinity or minus infinity to plus infinity, we should put a factor of half, because we have already halved the this interval, and it is a d2 d alpha 2, and then we have a exponential minus alpha x square dx 0 to infinity, and this is nothing but root over pi over alpha, okay, with this half factor included there. So, we can do these integral and can land up with this simple formula for n particles. So, for so this for one particle. So, for n particles. Now, there is a correction factor that the Sackur and Tetrode they introduced, which gives a v to the power n and this n factorial, and then a 2 pi m k t divided by h square whole to the power 3 n by 2. Okay. So, this is the total partition function, and you can write it as a the one particle partition function. So, this is the canonical partition function, where there is a permutation this n factorial being used, and this is just to make sure that each of those exchanges of particle does not give you a distinct state, but it is actually the same state with some phase factor. So, this n factorial cuts down the number of permutations possible for such exchanges, and because these exchanges are included here, this should correspond, or rather should take into account the indistinguishability of particles, and should give you the correct formula for any of these parameters that you are interested in, particularly the entropy that they were interested in the quantum mechanical limit. Okay. So, again you can use f equal to minus k t log z, and one can find out what the free energy is, which comes out as minus n k t log of v over n, and a plus a 3 by 2 log of t, plus 1 plus 3 by 2 log of this, just writing it, taking this log and so on, and there is a h square, and there is a big bracket here. So, that is the free energy that one gets, and you can also write down the partition function, which you can do it either by from the this z itself, or what you can do is that that this is nothing but equal to 3 by 2 n k t, and then of course, your S is equal to E u minus f by t, u minus f by t, and this gives you a nice formula, which is a correct formula, because of the reason that we have seen last day. So, this is V over n plus 3 by 2 log of 2 pi m k t and h square plus 5 by 2 and so on. So, this is the formula for that, and then S over n k, or which is n k is often written as R, the universal gas constant, is equal to V over n lambda cube plus 5 by 2, and we just write it lambda with a lambda t, where lambda t is called as a thermal de Broglie wavelength. And this has a form which is given by h over root over 2 pi m k t. Okay. And this will play some role in distinguishing classical stat mech from quantum stat mech, and we will come to that in just a while. And so, the gas is really still classical. However, this n factorial that is included in the partition function, that excludes overcounting, that is the exchange of particles, that gives rise to a new state, that is not taken into account by this n factorial. Gibbs paradox, it was similar to the spirit of how the Gibbs paradox was fixed, which we have discussed last day, and in which inside the expression for entropy, this n was introduced, or n factorial was introduced, and then Stirling's approximation was applied, and which gave rise to the correct formula for the entropy, at least in terms of its extensiveness. Okay. And here you can see that the extensiveness is maintained, that is, if you increase n, v and e by a factor, by a certain factor, the entropy enhances, or rather gets multiplied by that factor as well. Okay. So, even though it is like we are doing it on a classical gas, classical ideal gas, but this correct counting is being introduced. So, I write that because it is an important comment. And I told you what this correct counting means, that is to exclude the over counting of states due to the exchange of the particle. Okay. All right. So, this is called as the Sackur-Tetrode equation, and then if you really apply it to the Gibbs paradox with this entropy. So, this entropy, let us call it as the equation 1, and this equation 1 would be applied to Gibbs paradox, that is mixing of gases. So, we again just draw that same picture just to remind you that you have N1 V1 T and N2 V2 T, that is there at the same temperature, and we are allowing the mixing of the two gases. So, this goes from a situation when the partition is removed, and you have still T and then N1 plus N2 and V1 plus V2. Okay. So, this is before mixing and after mixing. We have two ideal gases there in the two chambers, and these chambers have these number of particles, volume and temperature to be given by N1 V1 T and N2 V2 T, and after they are mixed there is this T is still the same, and then N1 plus N2 and V1 plus V2. So, the available volume is that. So, S initial is we have written it initial even earlier. So, this is equal to N1 R. I am just using this the number of moles, or you can write it as N k. That's so it is N1 k and log of V1 by n1 plus 3 by 2 log t. We can combine these all the other constant into C. This other constant is also an important quantity in the context, because that gives you some S0 or the entropy that is independent of all these relevant parameters. So, this is the first one for the first gas, and then it is Nk, and then we have a log of V 2 by N2 plus 3 by 2 log of T plus some constant again, which is independent of all these things. So, we can simply add them up, and what we get is the N1 plus N2 K, and then we have a log of now what we do is that we replace V by the equation of state, which is P v equal to N k t, and then we have this as P k t over P. So, this is replacing this, and then we have a 3 by 2 ln T plus some constant. Okay. So, this is the initial entropy of the gas, that is before mixing, and final entropy of the gas, which is easy to determine. So, that is corresponding to N 1 plus N 2 number of particles. So, we have N 1 plus N 2 into K, and then we have log of V 1 plus V 2 divided by N 1 plus N 2, and then you have 3 by 2 log of T, which would remain constant, and plus some C. Now, you see that if you again use the equation of state, that is a pressure at V 1 plus V 2 equal to some N 1 plus N 2 k T. Then what we see is that we get S initial equal to S final, and which should get. So, the idea was to start taking care of the overcounting right from the beginning at the definition of the this partition function, and hence arrive at this expression for entropy, which is known as the Sackur-Tetrode equation. And this equation not only has the extensive nature, now you see that the extensive nature is inbuilt here, and this is called as, so equation 1 is called as Sackur-Tetrode equation. All right. So, this is the equation, and as we said that this has been in terms of historical development, it has a lot of value, because it was developed independently of either Einstein's photoelectric effect or the Planck's distribution formula. It was purely from a thermodynamic point of view. So, either you can do it from a microcanonical perspective. Here we had shown in from a canonical perspective. In the microcanonical perspective, you would have calculated the number of microstates and take the log of that, multiply it by k to get the entropy directly. Here of course, we had gone through the canonical path and have calculated the entropy. The entropy not only is extensive, when you have these two identical gases kept in two chambers and they are allowed to mix, there should be no change in entropy, which is what. So, the entropy of mixing, which we have defined earlier, is 0, which means there is a correct result. Okay. So, in the classical gas, if the overcounting is properly taken into account, it gives you the right entropy, and that is what this equation tells you. Okay. All right. So, let us now go to a few differences between classical stat-mech and classical and quantum stat-mech. We will write it together. Okay, so how do we sort of enumerate the differences? And there are many differences, in fact, and we are just highlighting some of the important ones and the ones that are of relevance to us. All right. So, we need to, of course, as you understand, some of the classical ideas that we have developed, they need to be modified in order to incorporate the indistinguishability of particles. Okay. One of the things that is of importance is that the positional coordinate, momenta and energy are quantized in quantum mechanics. Okay. And these quantization should actually take the scale of the Planck's constant h or h cross. The h cross is equal to h over 2 pi. Okay. So, it is so most of the time this is used, this h cross is used, or even in some cases h is used. Now, you have to understand that there are quantization in some sense even in classical physics, in classical electrodynamics and so on. If you remember that if you take an organ pipe and want to know the frequencies, how the frequencies are they behave, or you want to take out different notes in the flute that you are familiar with, and there are these nu over 2L or nu over 4L are the quantization of the frequencies, where L is the length of the flute or that organ which emits sound. So, these are quantizations that are there, and whenever you solve a differential equation pertaining to certain boundary condition, you are bound to get such quantization. If you remember that if you have solved Laplace's equation for, say, for example, either a dielectric or a magnetic material, you got those results as these some constants, and then some function of r, and then some PL cos theta, where these are called the Legendre polynomials and so on. So, these L's, each of the allowed L's are going to be solutions for this problem. So, a superposition of all of them, they are also solutions of the problem. And so, these L equal to 1, so I am particularly talking about this Legendre polynomial for the this Laplace's equation. So, it is a PL cos theta, where L equal to 0, L equal to 1, or L equal to 2, etc. They are allowed solutions, and then you can also superpose them to get a solution which is the most general solution for this particular problem. So, for example, your V of r by solving a Laplace's equation, it gives you some form, if I remember it correctly, it is like A L R L plus B L by R L plus 1 and a P L cos theta. And this is a solution for both the electrostatic potential or as a magnetic potential, if you are talking about a magnetic case, magnetic scalar potential. And each of these L's can take values, as I said, 0, 1, 2. So, it seems that there is a quantization, or there is a discreteness there as well in the solutions. We are not talking about this kind of discreteness. The discreteness in energy or the discreteness in the angular momentum should carry a scale that is equal to the Planck's constant, which is h or h cross. Okay. So, that is one important thing. The second important thing is that we know that Q and P can be independently defined in classical mechanics. However, Q and P cannot be independently defined because of the uncertainty relation that we have. So, this delta Q delta P should be of the order of h cross, or one can write it a little more correctly as less than h cross by 2. This got nothing to do with the accuracy of the experiment. This is very inherent to the system, and every set of canonical observables have to follow this uncertainty relation. Okay. Which could be j phi, or it could be j means the angular momentum and the angle, corresponding angle, angular variable rather, and the energy and time. So, delta E delta T is again this follows this relation, delta E into delta T is equal to or less than equal to h cross by 2, delta j delta phi, where j is the angular momentum and phi is the angular variable, they also would conform to this. So, now let us take an example for say particle in a box. So, we have particle in a box, and this is the first thing that you always see. So, what it says is that the potential is 0 inside, and these walls are infinitely high. So, this v equal to actually infinity. So, which means that the particle is confined and it cannot escape on either side, and while it is inside there is no potential that it feels. Okay. So, it is like a free particle which is allowed to go anywhere between this, and it is associated with a wave and so on, and then we know that the quantization for this comes as p n, or the momentum is quantized as 2 pi over L n h cross and so on. So, where n is an integer. Okay. There is no extra degree of freedom. We actually have lost the position or positional degree of freedom, but it does not matter to us, because this n can be actually found out as p n L divided by 2 pi h cross, and there is no information about q. But when you actually do this sum over n, or sum over all the states, you can do an integral over this n, and this is equal to nothing but so this L by 2 pi h cross dp, and which is nothing but equal to dq dp by h. This is just a simple example for particle in a box, where even if you do not see the positional degree of freedom, that is actually there, and this L is it takes into account this this positional this uncertainty there and so on. So, in short, what we want to say is that if you remember that P and Q are 2 points in the not 2 points, just a point in the phase space. In the PQ space, there is a point here which is called as P0 Q0. Okay. And it is a sharply defined point, and we have developed many understanding of how to do an ensemble average, or how to define ensembles, and how to actually reconcile the statement of Liouville's theorem, etc., all in this description. And so, because of this uncertainty relation, now this point actually acquires a bit of fuzziness, and it is, let me draw it with a color, and this is that is now the area of this fuzzy object, which now looks squarish, is a multiplication of delta q and delta p, which is of the order of h cross. So, that is where the correspondence between classical mechanics and quantum mechanics, they are that is how they are established, that a point now becomes fuzzy and acquires certain region of space with an area equal to h or h cross. Okay. All right. So, let us look at some more differences with them and with between the two, and let us just talk about this two very importantly, which we have told many times earlier and as well as today, is the indistinguishability of particles. So, exchange of two particles does not give rise to a new state. Okay. This has to be properly taken into account. Okay. In classical mechanics, it was or classical statistics, it was taken as it would have given rise to a new state and so on. Okay. So, even within that, this exchange statistics, this is called as the exchange statistics. So, one needs to define an exchange statistics, and this exchange statistics gives rise to two kinds of particles. One is called as the fermions, which upon changing their mutual positions, they pick up a negative sign, that is a phase which is equal to pi, and there are other kind of particles which do not pick up a sign, and they, or rather they pick up a phase which is equal to 0. So, this 0 and pi phase, because of the interchange of particles, that give rise to two kinds of particles, quantum particles, that we have to talk about, and these two type of quantum particles have very different properties. Like for example, fermions obey Pauli exclusion principle, which means that no two fermions with the same quantum number can occupy a given energy state. So, this is called as a Pauli exclusion principle, and because of that, picking up a negative sign, one can write down the wave function, a many particle wave function for the fermions as a Slater determinant. We will see all of that, and bosons actually have no problem in occupying any number, basically no constraint on the number of particles occupying single particle states. So, this is a more stringent condition, because you see that if two fermions cannot allow one given energy state, that is like putting a hardcore condition that one electron, if it is already there, or one fermion, if it is already there, electrons are fermions. It is already there, then another electron or another fermion cannot come. So, that puts a constraint, and this constraint gives rise to a large number of very interesting properties for fermions which are not observed for bosons. On the other hand, since bosons actually like being together, in fact, we will show that this number fluctuation for bosons, they indicate that they actually like being together. This gives rise to another very important phenomena which has been observed experimentally, called as a Bose-Einstein condensation. So, they will all be part of our discussion of statistical mechanics. We just want to mention it here. So, these obey Fermi-Dirac statistics, and these obey Bose-Einstein statistics. And what could be more differences or other differences? One can really think of that in classical mechanics, one really talks about solving Newton's equation of motion. So, Newton's laws, and they would really mean all the three laws that we are aware of, and this means that F is equal to dP dt equal to m d2x dt2. And this means that if you solve this differential equation by integrating it twice, you can get x of t if you know the nature of f that is acting on the system, and this is what is done in the numerical procedure is followed in what is called as a molecular dynamics simulation and so on. So, one really sort of builds up x1 t1 at x2 t2 and all the way till xn tn. So, that sort of fixes the trajectory of the particle that it takes in the influence or under the effect of this force that acts on the system. On the other hand, in quantum mechanics, one talks about Schrodinger equation. We are of course talking about non-relativistic mechanics. So, where it is written as minus h square by 2m, and we write it in 3 dimensions. So, it is del square psi, it is called a Laplacian operator, plus v of r psi. Psi is a function of a vector r, and vector r can be x y z or r theta phi, depending on what kind of symmetry the system has, and this is E psi r. You can write it as the time dependent equation is written as I h cross del del t of psi r. And one solves this equation, and we are only sort of familiar with solving it in known situations where there is a closed solution, the time independent part of it mostly, and that is what you see in the first course of quantum mechanics, that you solve it for a number of problems such as particle in a box, such as hydrogen atoms, such as harmonic oscillator, and maybe more sort of systems such as say linear potential instead of a harmonic potential, a linear potential which gives rise to airy functions and so on. And some of these things are easier to do using an approximate method. For example, this linear potential or a slowly varying potential is usually done using WKB approximations. So, we can solve this in a variety of situations, and in a very different type of arbitrary situation. Even this one particle Schrodinger equation is not solvable, and one may resort to techniques, numerical techniques to solve this differential equation once again, just like the Newton's laws, and one finally gets what is known as psi r, and in this particular case it is if you take a time dependence, this is really a psi r t. V is taken to be time independent in the sense the potential is also time dependent. Then of course, you cannot solve this equation unless you have a very specific kind of time dependence, which is periodic time dependence. Then there are different methods of solving these things called as a Floquet formalism and so on and so forth. Okay. So, what you find out is that you find out this psi of r t by itself, which is the solution of this differential equation. By itself, psi of r t does not have any physical significance. Okay. It only acquires physical significance if you talk about the quantity called as a probability density, and which is given as psi of r t mod square, or probability current density, which is defined as say j, which is like r t, and this is if I remember the prefactors correctly, it is like this. So, it is a psi star r t del psi r t minus del psi r t. So, psi star, where psi is the wave function which is in general complex, and by itself, as I said, psi is just a mathematical function. It has no physical meaning, but when you talk about this mod psi square, it acquires a physical meaning that denotes the probability of finding a particle in certain region of space and time, which is r and t, and one can also calculate the this probability current density if you know this psi and psi star. So, psi is in general complex, as you can understand that. So, that is why psi and psi star could be distinct. Which will tell you that the probability current density would exist if psi is completely real in certain situation, which it does as you solve this particle barrier penetration problem. If you have the wave function to be completely real, there is no current associated with it, and it is called as an evanescent wave instead of a propagating wave. Okay. So, another very important thing is that two kinds of averages appear. What do I mean by two kind of averages? One is of course the quantum mechanical average, which is the we will just see in a while that what is a quantum mechanical average. and we also have a statistical average or the ensemble average, okay, statistical or the ensemble average. So, instead of just one average, which is ensemble average in classical statistical mechanics, here one needs to worry about two kinds of averages, or there is a double averaging that comes into picture, where the quantum mechanical average or the expectation values of operators, they also have to be taken into account, and as well you need to average over the ensembles. Okay. So, this is something that we are going to discuss. Now, let us see that what is the limiting case of quantum statistical mechanics or quantum mechanics, quantum stat mech maybe. That is, the ones that we have learned so far, are they all wrong, or in some limiting case it is true. We have said that in the limiting case it is true, but let us see it more carefully. And so, we write this delta x delta p is equal to of the order of h cross. You can write it h cross by 2 or less than h cross by 2, they mean the same thing. So, say this one delta x for a particle, okay, for a point particle, or for a particle with some finite dimensions, what could be delta x? So, if you think of just a small billiard ball like structure which has a radius r. So, the maximum uncertainty or the maximum uncertainty in the measurement of the position is the radius itself. Okay. So, this delta x, the maximum delta x is say for example, is like the r, which is the size of the object. It can be a cubic object or it can be a spherical object. Just for convenience, we have taken it to be a spherical object, but it can be as a cubic object as well. And this one, this p is the momentum, which is so the classical limit demands that these quantities should be much greater than r into p, should be much greater than h cross, right, because if h cross is comparable to this product, then we are in the quantum regime, and we are talking about the classical limit of this. So, r cross r dot p should be equal to h. So, r should be much greater than h over p or h cross over p, it does not matter. So, this is this h over p is of the order of lambda, where lambda is called as the de Broglie wavelength. So, what de Broglie proposed is that when it was fairly clear at the beginning era of quantum development of quantum physics, that there are particle descriptions and there are wave descriptions of the same experiment. Like for example, photons, they undergo interference experiments, Young's double slit experiments or diffraction, which show up the wave phenomena, whereas there are Compton effect and there are photoelectric effect, which shows the particle phenomena, because you apply the conservation of energy and so on, as if they are like hard billiard balls. They are electron is colliding with photons, or in situations where they are really taken as hard spheres, and you talk about the energy and momentum conservation relation. Of course, we talk about these are elastic scatterings, and so there has to be a reconciliation between the wave description and particle description, and de Broglie came up exactly with that when he said that the momentum of a particle p, which is say equal to mv in the non-relativistic case, should be related to the wavelength of the wave through this relation. Okay. So, lambda is equal to h over p is what he said, and this is called as a de Broglie wavelength. So, it is h over p if we ignore this h cross and h, which is simply a factor of 2 pi, then this is really equal to much greater than the wavelength associated with the wave. So, the size of the particle has to be very large as compared to a wavelength that could be associated with the particle. So, this is the classical limit. Now, if you think of gas or a sort of a system and try to fill up the system by all these hard spheres, or for just for a moment think that we have cubes which have a volume equal to r cube, and we need n such r cubes. There could be a 4/3 factor if you take into account the sphere, but let us forget that, and so r cube into n should be equal to v. So, we have a system with a volume v, and we are completely filling it up with objects that have volume r cube, and n of them that are going to fill this entire volume. So, this tells you that r is equal to which is v by n to the power 1/3. So, this is r to the r equal to v by n to the power 1/3. So, this is v by n is nothing but inverse of the density. So, there is a density to the power minus 1/3 that comes here, and this when you apply equipartition theorem, so you have a 1 over 2 m and a p square, this is equal to some E, which is equal to some 3 by 2 k T, and that tells you that this P is equal to like a root over 3 m k T. So, this lambda that you get is h over P, and this is like root over 3 m k T. Well, we have written it with the thermal de Broglie, which is slightly different than that. And so, the where classical limit is valid, when this v by n whole to the power 1/3 is much greater than this particular thing. Okay. So, this is what we have told. So, this condition translates to, so r much greater than lambda, that translates to, so we have calculated r, which is v by n whole to the power 1/3, and we have also calculated lambda, which is h divided by 3 m k T. So, putting it into this r much greater than lambda, we get root over h divided by 3 m k T. Okay. So, this tells one thing, that the classical limit is valid one when temperature is high, which means the thermal effects dominate over the quantum effects, and the other is that we have the density to be small. Okay. So, the density is here, which is n divided by v is equal to the density. So, when the density is small, that is inverse of this is small, then of course, this is going to be valid, or when temperature is large. So, the limit of the quantum statistical mechanics is the classical statistics. So, classical statistical mechanics is obtained as a limiting case of quantum stat mech. Okay. So, which means that at very large temperature, the distinguishability goes away and the particles become indistinguishable. Okay. And at very low temperature, the indistinguishability sets in, which means that the particles are to be treated alike, and you cannot give a sort of name, texture or color to each of the particles that are under consideration. Okay. I will stop here. Thank you.